the next two lectures we will discuss in detail about some case studies where I will show you some application of risk analysis methodologies on different problems quickly. If we looked at the application aspect of risk analysis on HSE, interestingly we will try to apply what we call as a fault tree analysis for offshore drilling operation problems as one of the case study. I will discuss very quickly the case study on Gulf of Mexico Macondo well blowout which occurred in the year April 2010. I will show you how a fault tree analysis is performed for loss of the well control for this specific accident scenario. I will also show you the next case study which we will discuss failure mode and effect analysis, what we call as an FMEA on the subsea blowout preventer. So, we have done a design FMEA on the BOP which will be discussed in this lecture. Based on the two case studies, we will give some recommendations for safe operating procedure for offshore drilling which will be summarized at the end of these two lectures. If we look at the overall methodology of risk analysis applied to drilling procedures, the methodology is simple in the 4 modules as expressed here. First, identify the potential failure factors. So, identifying the potential failure factors, you must know thoroughly the process and the design principles involved in the elements. After identifying the potential failure factors, categorize them depending upon which factors are having high risk values. That is, categorize the potential failure factors to form what we call as a risk analysis hierarchies. You have got to arrange the risk factors related to these potential factors in an ascending order. Then model and estimate the probability of risk using either FTA or FMEA methods. After doing the analysis, interpret the analysis results and then prepare what we call as a detailed report based on your study. So, methodology on risk analysis has got 4 different modules. In the first module, you will identify the potential failure factors responsible for that failure. You will categorize them and prioritize them based on the risk factors in an hierarchical manner. You will then model and estimate the probability of risk involved in these failure factors, then interpret the analysis results and prepare a detailed summary report based on your analysis. If we look at the stages of risk analysis involved in these case studies, basically there are 3 stages where we are connecting our risk analysis to the applied problem. One is what we call identifying the risk, which is risk identification. Then we do what we call a QRA, which is a quantitative risk analysis. In this platform, we quantify the risk involved in the process. The third will be what is our planning and methodology guideline for risk mitigation in the problem. If we look at the offshore drilling process, let us quickly look at an overview of the offshore drilling. As I said, before we do the analysis, we must understand the overview of the whole process. For the case study of offshore drilling, let us look at this figure. I am having a semi-submersible drilling rig which is being used for drilling at a specific field. This is basically the drilling case. This is what we call as a marine drilling riser. I have provided here a subsea blowout preventer which is shown in yellow color. This is my indication of the sea floor. Inside the sea floor, I have got different kinds of casing for drilling. This is 28-inch casing, followed by a 20-inch casing, followed by a 13 3/8-inch casing, followed by a 9 5/8-inch casing. This is where I find my oil and gas reservoir from which I am actually drilling. The overview of the process of offshore drilling and operation involve the following different stages. Setting up of the rig is the first process, let us say. You then install the marine drilling facility, then install the marine drilling riser, install the blowout preventer, then install the drilling casing and then perform drilling. If you look at the safety measures related to offshore drilling operations, the safety measures can be categorized easily using this flow chart. The drilling system essentially consists of two control mechanisms. One is what we call as a well control systems, that is the control systems available in the well. The other control systems and support systems are available on the drilling area. Combined together is what we call as a drilling system. If you look at the well control system in detail, the well control system comprises of the blowout preventer system and equipment, the LMRP, the marine drilling riser, a diverter, a choke and kill, an auxiliary well control equipment, well circulation system and equipment, well circulations and degasification systems, secondary well control systems comprising auto shear, emergency disconnect system, ROV interface and acoustic level. If you look at the drill support systems, this consists of the derrick and a mast and a supporting structure, the mud conditioning at mud separators, heave compensation devices, riser tensioning systems, rotary power swivels, drawwork and hoisting equipments, lifting, handling and cranes used for handling, pipe handling equipments, BOP transporters, BOP skidders, hydrocarbon waste disposal systems, cementing equipments, vent stack, flare boom, burners and hydraulic power units. We must clearly understand the distinct differences between the drilling support systems and the well control systems if we really want to look into the safety aspect of drilling operation. Let us ask a question: what are the major problems and risks that are seen during a drilling operation? There are many risks involved in a drilling operation. Very critical of them are mentioned here. Foremost could be a drill pipe sticking and the pipe failure. The major problem can also occur due to lost circulation. It can be either from hole deviation and borehole instability. It can also occur from mud contamination. It can also be due to formation damage. It can also result from what we call as a drill bit failure. These are the major problems and risks involved in offshore drilling. Let us quickly see a few of them. What do you understand by drill pipe sticking risk? The drill pipe can stick to the casing or the formation by three different manners. There is a possibility that the sticking can be differential. You can see the scaled form here is of a different intensity and thickness compared to this. So, when you try to move the drill pipe up and down, there is a possibility that the drill pipe can stick on to the surface here. This is what we call as differential sticking. Sometimes there can be a faulted zone occurring in between the drilling casing. This is what we call as fractured or a faulted zone, and in such cases drill pipe sticking can also occur. In some situation there can be what we call an unconsolidated zone being drilled through, and there is always a caving in from the unconsolidated zone which will start blocking the drill pipe sticking. So, these are what we call the drill pipe sticking risk, which is referred by John Fuller et al. In Panvel Corporation 2008. Further, It can also occur due to what we call a poor hole cleaning. You can see here a residual deposit in the borehole, and this has not been cleaned or drifted properly, and this can also result in what we call drill pipe sticking. Sometimes this can also occur due to what is called a key seating. The key may not seat properly, and due to that the drill pipe can also stick. Now let us see how we are going to do a fault tree analysis for the drilling risk and the time loss involved. We have already discussed a network layout of a fault tree analysis in the previous module. I think you must have gone through what are the fundamentals of a fault tree analysis. On the basis of that discussion, we try to do a fault tree analysis now for a drilling risk for the specific problem. The symbols what we will use here will be the following. I will describe the event with a closed rectangle. If there are lower events which require both of them to occur for a successive event, I will use a symbol of this order. If any one of them need to occur to make the drilling risk possible, I will use this symbol. These are standard symbols of logic gates being used in a fault tree analysis, which we have discussed in detail in the previous modules. Let us look at the fault tree here as I am drawing it for a drilling risk. I am now addressing drilling problems and loss of time both. The drilling risk can occur mainly from three sources. It can be a drill pipe sticking, it can be a drill pipe failure, it can be a drill bit failure. If we look at the symbol here, either one of them is sufficient to cause a drilling risk. So, I am using an OR gate here. So, either one of them is sufficient to cause what we call as a drilling problem or a drilling risk. It can be either due to drill pipe sticking or due to drill pipe failure or due to drill bit failure. So, I have started the float tree diagram from the top like this. Now, when you look at the drill pipe sticking, the reasons for a failure of this order can be from different sources. It can be either due to differential pressure or due to low lubricity, which results in a formation of a mud cake. The mud cake can also be very thick being formed. It can be also due to excessive embedded pipe length inside. So, either one of them could be responsible for a drill pipe sticking, or it can be due to a differential pressure which can be caused due to poor hole cleaning and formation fluids entering the annular space. It can be also due to loss of drilling mud. The loss of drilling mud further can be due to loss of fluid overbalance or drill pipe stuck in the fractured or a faulted zone. Both of them are necessary to cause what we call the loss of drilling mud. That is why I have used an AND gate here. The loss of fluid overbalance can either occur from a loss of primary containment or due to failure cementation, which we call the failure of a casing. Either failure of a casing or loss of fluid overbalance can cause the loss of fluid overbalance. Put together on the fractured and faulted zone will cause loss of drilling mud. Either the loss of drilling mud or poor hole cleaning can result in a differential pressure. Differential pressure put together with either one of them can result in drill pipe sticking. This is how a fault tree analysis can be read. So, ladies and gentlemen, based on your experience and literature reading, you should be able to identify the different events responsible for a specific subclass of failure. Let us look at the drill pipe failure. When you look at the drill pipe failure as an event of failure, it can be either due to a fatigue in the drill pipe, or it can be a twist off of the drill pipe, or it can be caused due to what we call as a key seating. we look at the drill bit failure, it can happen when the varying of cutting of edges and either one of them is occurring jointly with the varying of cutting of edges. The varying of cutting edges can also jointly occur with improper hard formation or at a higher rate of penetration. Both of them put together, either higher rate of penetration along with varying of cutting edge or improper load at hard formation along with the varying of cutting edge, can result in what we call as a drill bit failure. So, drilling risk can occur either due to drill pipe sticking or due to drill pipe failure or due to drill bit failure. This is an example of a fault tree analysis being carried out for a drilling risk and time loss. Now, based on this, let us try to classify the risks of these events, their likelihood and their consequences if at all they occur. The likelihood of every event is given in a 5-point scale. If the score is 1, then we can say there is no chance of that particular event occurring. If the score is 5, we can say there is a definite chance of that event occurring. So, the likelihood is nothing but a score given to these events as given from this scale factor of 5, whereas the impact factor of consequence based on the scale of again 5, where if I indicate 1, though there is a likelihood of any specific event, it will cause no impact. If I indicate a scale of 5, then the likelihood will have a major impact. After understanding this, let us look into the risks of different events: drill pipe sticking, lost circulation, hole deviation and borehole instability, and drilling pipe failure and drill bit failure. Based on the fault tree analysis done in the previous slide, I have grouped the risks into 4 headings. I said the drill pipe sticking can have a likelihood of somewhat likely, I have given a number 3. The time delay in operation can be one of the consequence if a drill pipe sticking occurs, and that consequence will have a major impact. The consequence of drill pipe sticking can also be resulting in a loss of capital investment. This will also have a financial loss which will have an impact of a scale of 5. So, the overall score of risk is nothing but the product of likelihood and impact. So, 3 into 5 gives me 15, as well as 3 into 5 gives me 15. So, the drill pipe sticking gives me overall score of 15. Look at the lost circulation. The likelihood of lost circulation in a drilling process is definite, it will always happen. If at all this happens, the consequence will result in uncontrolled flow into the formation, and the impact of that will be significant. Therefore, the overall score of a lost circulation in a drilling failure analysis is 20, which is higher than that of a drilling pipe sticking. So, ladies and gentlemen, based on the fault tree analysis, I am trying to prioritize the order of risk involved in different events as studied earlier. Similarly, if we look at the borehole instability, the likelihood in drilling formation is generally very likely, and the hole deviates from the vertical or a planned course of drilling, which will have a very serious impact in your whole process. So, the overall score of this could be close to 20, whereas the drilling pipe failure or a drill bit failure will have a very less likelihood of 3, and the consequence can be resulting in a score of either 3 or 12, depending upon what kind of consequence you are envisaging for a drill bit failure. So, if the significance of the overall score is exceeding 14, then the risk is considered to be significant. For example, if we read the table back with this number 14, then the overall score of drill pipe sticking is 15, the lost circulation is 20, the borehole instability is 20. It means these kind of events of drill of risking are very significant. Therefore, we should have a strategy to be developed to control failure due to these kinds of risk occurrence. If the risk score is between 5 to 14, then we must keep on monitoring it continuously, so that it should not create a significant risk subsequently. For example, the change of drill bit can be one of such example in this, where the overall score is very low. So, we should constantly monitor the drill bit for its requirement of change of the drill bit. We will now take up the second case study, which is on the Gulf of Mexico Macondo well blowout in the month of April 2010. There are some key findings related to this blowout. The right hand side is a picture what you see, a schematic view of this blowout. This is my drilling rig, this is my riser, this is my blowout preventer, this is my sea floor. I am keeping my BOP just above the sea floor. These are my casing, this is my reservoir which I am showing in the yellow color. These are the flow of the reservoir into my drill well. The key findings found from the literature analysis are the following. The annular cement barrier did not isolate the hydrocarbon flowing into the casing, it should have isolated the hydrocarbon. The second important reason for this blowout is the shoe track barriers did not isolate the hydrocarbon entry here. Thirdly, and very interestingly, the negative pressure test which has been carried out was accepted, although the well integrity was not established completely. The influx coming in the riser was not recognized until the hydrocarbons entered the riser. The well control response being installed on the top of the rig failed to regain the control of the well. They were not effectively working at the time of the blowout occurred in the month of April 2010. The diversion to the mud gas separator, which is being located on the top side, resulted in the gas venting onto the rig. The fire and gas system did not prevent the hydrocarbon ignition coming from the riser. The BOP emergency mode did not seal the well completely. So, all these consequence of events resulted in a blowout of the Macondo well in Gulf of Mexico in the year April 2010. Let us quickly do a fault tree analysis for the BP disaster occurred in April 2010. So, I am using the same symbols for event and the OR gates, which I discussed in the previous case study. Let us say the topmost event which I am looking or trying to address is loss of the well control, which resulted in explosion and fire of what we call as the BP disaster. The BP disaster could have been occurred as a combination of well fluids reaching the rig and the ignition source being present at that time. The well fluids reaching the rig could be due to any one of these events. The wellhead seal assembly has failed, or loss of primary well control, or instability of secondary well control and BOP has combined this to have the well fluids reaching the rig. When you look at the loss of primary well control or the well design and construction procedures, this can be also due to well system failure or well control procedure errors. Put together result in loss of primary well control. The well system failure can be either due to the casing failure or cementing failure. The well control procedure error can be due to failure to detect the kick or unbalanced mud column or the mud removal length. So, looking into a very brief analysis of FTA for the BP disaster, we are able to identify the important events which could cause or which could result in this disaster. Based on that, the probability of event occurring in the BP disaster is being tabulated. we have set event number as A, B, C, D, J, K, L, M, N, etc. For example, event A could be loss of well control, explosion and fire. The probability of well control loss could be 2% on a scale. Well fluids reaching rig can be a 5% probability of occurrence. The presence of ignition source can be 7%. Wellhead seal assembly and overload can be hardly 1%. Loss of primary well control can be about 1.2%. Like this, we have started giving the probability of occurrence of every event associated with a specific number. Ladies and gentlemen, you can see here the highest number is given for well fluids reaching the rig, which has resulted in an explosion for sure, and mud removal length or the mud column imbalance has also caused an important reason for this failure. So, the higher numbers of probability are given for these two, the lowest numbers are given for overload of wellhead assembly, instability to control the accident, and the well system failure as an overall. Once the probability numbers are assessed, now we can compute what we call as probability of failure or probability of occurrence of the topmost event. For an AND gate, if you see in the logic tree, the equation is 1 minus probability of that event product of 1 minus probability of the B event, because for AND gate you must at least have 2 events A and B. For an OR gate can either have A or B, therefore the formula used is 1 minus the product of these two probabilities. So, after looking at the fault tree, identifying the events A and B, looking at the gates and OR gate, substitute in this equation, try to fill up. I can just explain one value for your computation. For example, let us look at 1 minus P of A product of 1 minus P of B. A is an event of probability 2, B is an event of probability 5. So, I said 1 minus probability of A 0.98, 1 minus probability of B 0.95, I worked out a product. Similarly, I can do for all the events of P of A, P of B, P of C, P of D and so on, and try to get the joint probability of occurrence of the topmost event, which is around 77.88%. So, from the analysis what we carried out, it tells me that the probability of failure of BOP or probability of this disaster is about 78%, which has occurred in reality on April 2010. You can also do another case study by explaining what we call as a failure mode and effect analysis on a subsea blowout preventer. FMEA methodology basically defines the BOP system to be evaluated, the functional relation of the components of the system and their performance requirements. Then, based on this definition and the functional relationship, it establishes the level of analysis. You have to identify the failure modes, their cause and their effects and the relative importance. Then we will identify the failure detection, the rectification and isolation provisions and methods. You will also identify the design and operating provision against such failures. Then you will summarize and recommend the corrective actions, then issue a report based on your FMEA study. These are the methodologies by which I can prepare what I call as an FMEA study. I will now apply this study for a subsea blowout preventer of a BOP. To understand the FMEA thoroughly applied on a BOP, let us first look at what are the different components of a blowout preventer. The blowout preventer typically has many critical components. The first one from the bottom, this is your operation on the top side, this is your bottom end. The wellhead connector is located at the bottom. The lower test ramps are located just above the wellhead connector. Above that are what we call as variable bore ramps. Above that are upper variable bore ramps. above that are the casing shear rams, and above that are basically the blind shear rams. So, blowout preventer is actually a vertical stack of different kinds of rams provided one above the other. Now, let us look into the analysis of failures through an FMEA study applied on this problem. All possible failure modes should be considered for the analysis. You must also look for a premature operation. You must look for failure to operate when required, that is also a possibility. You should also look for intermittent operation, the operation starts and then it fails. You should also look for failure to cease operation, that is you are not able to stop the operation when you require to stop the operation. You should also look for failure during operation. If you look at the annular BOP, the parts used in FMEA study, this is the first part what I am looking at is a packer. The actual component used in the annular BOP is an elastometric donut. The second component is nothing but a piston which you see in a white color. The third component is actually an O-seal rubber which is being used here. Now, the other operational conditions what we have got to look into, which we have got to opening and closing pressure, which we have got to measure at this and these two locations respectively. This is an FMEA sheet prepared for the annular BOP. You have seen the working of a BOP very briefly. You have seen the components of an annular BOP as 1, 2, 3 and 4 and 5 are the pressure requirements for opening and closing the valve. So, these are the 3 components which I am mentioning here. We will look into detail of FMEA. Thank you.